In the previous video, we began hearing of Plato's lost treasure. The story involved platonic solids and magical fairies, sunken treasure chests, all sorts of crazy stuff. If you haven't seen that video, you probably want to watch it before you watch this video to make this one make sense. We left off shortly after completing level 1, which involved completely solving our tetrahedron puzzle, and we began level 2 with a similar puzzle on an octahedron. Here's our octahedron with all the vertices labeled. Note that each vertex also contains a counter, all initially set to 0, and we have the ability to touch faces to increase the value of all vertices on that face by 1, or decrease the value of all vertices on that face by 1. We can rotate the octahedron in such a way that we'll be able to touch any of the different faces, and our goal is to program this code onto the vertices of this solid. As we saw with the tetrahedron, dealing with the two-dimensional version of this shape makes life a little bit easier. So I'm going to reset the vertices all to their initial counts of 0, and then unfold the shape to deal with the two-dimensional version. It's hard to keep track of all the vertices in the animation, so here's a quick replay in case it helps. Now that we have our two-dimensional model, we can start working towards a solution. Following the methods that we developed with the tetrahedron, we can look for a +1 - 1 combo to create a new version of the Rubik's Cube algorithm, or just employ linear algebra. I'm going to start with linear algebra. So first we name each of the 8 different faces, and then we set up an equation for each of the 6 vertices, tracking which faces affect the counter on each vertex. That gives us this system of linear equations, which we plug our desired code into and solve. You solve it however you want. I'm going to row reduce an augmented matrix to get it into reduced row echelon form. As we watch these elementary row operations, you might notice that the bottom 2 rows completely cancel out. Informally, that just means that they're dependent upon the rows above them, so we kind of get them for free. In reduced row echelon form, if we don't count our augmented column, we have 4 columns that don't contain any of the rows leading ones, so these 4 columns represent free variables. In other words, we can hit the faces E, F, G, and H as many times as we want. It doesn't matter at all. There'll still be some amount of times we can hit A, B, C, and D in order to get our code onto the octahedron. Since E, F, G, and H can be anything we want, let's make life easy and just pick 0 for all those values. Using those values for E, F, G, and H, we get answers for A, B, C, and D immediately, which gives us a solution set that we can check out on our two-dimensional model. Just like the matrix promised it would, pressing these faces produces the code we are looking for on the octahedron. Much like with the tetrahedron in level 1, when we succeed in opening the octahedron, out pops a fairy who informs us to complete level 2, we need to find a condition that is both necessary and sufficient for a code on the octahedron to be realizable. Again, not all codes are even possible. The fairy wants to know which ones are and which ones aren't. So where to begin? Well, you might be wondering why I didn't come up with the +1 - 1 combo to get the desired code onto the octahedron. After all, that method was significantly easier when we were dealing with the tetrahedron, so why not use it here with the octahedron? The answer lies in a fundamental difference in the geometry of these two solids. With the tetrahedron, any 2 vertices are adjacent. So if we can form a +1 - 1 combo, it's easy enough to kind of traverse across the different vertices of the solid, setting them to the correct code one at a time without messing up anything we've already set. However, with the octahedron, if we increase the vertices on a face by 1 and decrease the vertices on an adjacent face by 1, it will again leave us with the +1 - 1 combo. However, the affected vertices aren't adjacent, they're opposite each other. That's important because it prevents us from using a strategy analogous to the one we used for the tetrahedron. Think about it like this. We could set L by messing up R, and then go try to fix R, but unfortunately doing so would mess up L. This +1 - 1 combo is no good. Fortunately, there's a solution. The fact that an octahedron has more faces, 8, than vertices, 6, gives us a little wiggle room. Consider this algorithm. Let's first set U to its appropriate value by using any of the 4 faces in the northern hemisphere of our octahedron. A, because why not? Now we want to set any vertex other than the one opposite U, so other than D, using a face that will not mess up U. So I don't know, maybe we'll do B next. B lies on 4 different faces, 2 of them in the northern half, 2 of them in the southern half, but we have to avoid the 2 in the northern half so as to not mess up U. So let's choose face B to set vertex B to its appropriate level. Rather than think about which vertex to set next, let's think about which faces we can use. We don't want to mess up U, so in addition to excluding A and F, we also can't use G or H. And we don't want to mess up vertex B, so in addition to A and F, we can't use faces B or E. That only leaves two faces, face C and face D. We can use C to fix vertex L, and then use D to fix vertex R. And you're like, okay, cool, you got 4 of the 6 vertices set to the correct digit of the code, but now you're out of faces. Touching any of the 8 faces will change one of those 4 digits. And that's true, but look again, not only do we have 4 digits of the code, we actually have all 6. And you're like, yeah, all right, great. It's easy to make things work out really nice when it's your problem. And I'm like, look, it's not my problem, it's Plato's problem. If I had lost treasure, I wouldn't be trying to make money on YouTube. And furthermore, the remaining 2 vertices containing the correct digit of the code is not a coincidence. It has to happen. Let me show you how. Notice that faces A, F, G, and H are the 4 that affect vertex U. If we consider the vertex opposite U, so D, the faces affecting it are B, C, D, and E, the complement of the faces affecting U. And that's not just true for U and D. The faces affecting any 2 vertices that are opposite each other are complements of each other. I probably don't even need to color code and animate that. There's 4 faces on the left side of the octahedron that affect L, and 4 faces on the right side of the octahedron that affect R. Similarly, the 4 faces on the front side of the octahedron affect F, and the 4 faces on the back side of the octahedron affect B. And maybe you're like, yeah, I see that, but what does that have to do with the code? Well, because we have these complementary pairs, pressing any face is going to change exactly one of U or D. And it's also going to change exactly one of L or R, and one of F or B. If you prefer algebra, you can see this by summing the equations that produced our augmented matrix. The fact that in our desired code, U plus D, L plus R, and F plus B were all equal to 13 was not a coincidence. Pressing any face affects these sums equally, so a necessary condition for a code being realizable is that these sums agree. Okay, but is this necessary condition sufficient? Absolutely. Just go back to our algorithm. These series of steps allow us to properly set U, B, and L, one vertex in each of the 3 opposite vertex pair. The minute we set R to its correct value, D and F must be set correctly, because U plus D and F plus B are always equal to L plus R. Anytime we have a code that satisfies our necessary condition, our algorithm can achieve that code, so our necessary condition is sufficient for a code being achievable. It's worth pointing out that having the 3 opposite vertex pair sums being equal makes the sum of all the vertices a multiple of 3, so this condition, which might also seem necessary, is already accounted for. We've got our answer for the fairy, we're done with level 2. In level 3, we take on the icosahedron, which might sound and look kind of scary, but it's actually going to be super easy. We're given this code to program onto the vertices, but before you go looking for a solution using some huge matrix, look at the net effect of pressing these faces in this manner. Only 2 vertices changed, and those vertices are adjacent, one increasing by 1 and one decreasing by 1. We have a +1 -1 combo on adjacent vertices of the icosahedron, and there's nothing special about these 2 vertices. We can come up with a +1 -1 combo for any adjacent vertices. The symmetry of this shape might be enough to convince you of that fact, but in case it's not, here's an explicit algorithm for increasing the count on one vertex and decreasing the count on an adjacent vertex. Start with the edge that connects these 2 vertices. Then pick either of the 2 faces containing this edge. It doesn't matter which one. We're not going to press that face, but the remaining vertex on that face will be the center of all the changes that we make. That center vertex lies on 5 different faces, one of which we already said we weren't changing. The other 4 will change. To figure out if we're going to press these faces positively or negatively, we first find the face that contains the vertex that we want to end up being our +1. We're going to press that face positively. Similarly, the face containing the vertex that we want to end up -1, we're going to press negatively. Of the remaining 2 faces, one is adjacent to the face that we pressed positively, we're going to press that negatively. And one is adjacent to the face that we pressed negatively, we're going to press that positively. Those 4 actions result in the desired +1 -1 combo. With this ability to increase or decrease a given vertex, changing only the value on an adjacent vertex, it'll be easy to program the given code. Note the code makes no mention of which numbers correspond with which vertices, so we can put them in any order we want. I'll put them in alphabetically, because why not? Much like we saw with the tetrahedron, because the +1 -1 combo doesn't change the sum of the counts on all the vertices, we want to start out by hitting any face we want enough times to make the sum of the counts on the vertices equal to the sum of the digits in the code. So maybe I choose face A and hit that 7 times. Now that the sum is right, we use the +1 -1 combo to decrease the count on vertex A by 3 while increasing the count on vertex B by 3. Now that vertex A is set correctly, our goal is to set vertex B correctly. We do so by changing vertex C. So we employ a different +1 -1 combo to decrease vertex B by 1, increasing vertex C by 1. And now we repeat. A and B are correct. We want to fix C. We do so by changing D. C needs to go down 4, so D goes up 4. We continue in this fashion using E to fix D, F to fix E, G to fix F, H to fix G, I to fix H, J to fix I, and K to fix J. The next step would be using L to fix K, but note that when I do so, by adding 4 to K and subtracting 4 from L, L also ends up fixed. Again, that's not a coincidence. The fact that we set the sum to its correct value guarantees that the last vertex will end up set correct if we set all the other vertices to their correct values. The fairy's back, again asking for a necessary and sufficient condition for a code to be realizable, which you might think will be a lot of extra work, but it's really not this time. The algorithm we just showed will work anytime the sum of the digits in the code is a multiple of 3, so that condition is sufficient for the code being realizable. Clearly that condition's necessary, because every time we touch a face, either the sum of the digits on the vertices increases by 3 or decreases by 3, so we have a necessary and sufficient condition, and we can move on to the next level. Level 4, which will be the final level, deals with the cube. Our goal is the same as in previous levels. First, we're given a code to try to program onto the vertices, and if we can successfully do so, to complete the level, we'll be asked for a necessary and sufficient condition for a code on the cube to be realizable. As in the previous levels, we'll use the two-dimensional unfolded version of the cube to set up equations showing which vertices are affected by which faces. That defines a matrix, which we can manipulate to better understand our solid. First things first, we can get the code onto the vertices of the cube by simply plugging the code into the augmented column in our matrix and solving that matrix using elementary row operations to get it into reduced row echelon form. We again end up with several blank rows, foreshadowing how some of the vertices will automatically end up being set correctly. We also see 2 columns without a leading 1, which means that the faces corresponding with these columns are free variables, giving us the freedom to set them to any value we want. We'll again choose 0 just to make life easy. This choice gives us the values for the rest of the faces, giving us a solution set that we can test out to open up the solid. The correct programming of the code leads to some unnecessary animation, which will eventually bring forth the fairy to ask her same question about a necessary and sufficient condition for a code to be realizable. To come up with these conditions, it'll help to have both a 2- and 3-dimensional rendering of the cube to reference. We'll also want to make use of the matrix that we came up with, showing the relationship between the faces and the counters on each vertex. If you were paying attention back in level 2, when we were dealing with the octahedron, you might notice that again, faces affecting vertices that are opposite each other are complements of each other. In other words, if I take vertices that are opposite each other, C and E for example, the faces affecting C are U, B, and L, and the faces affecting E are the complement of those faces, so F, R, and D. And that's not specific to vertices C and E. As we see with our matrix, if we pair up opposite vertices, touching any face affects exactly one of the 2 vertices in each pair. So for a code to be realizable, it's necessary that the sum of the counts on opposite vertices all be equal. Okay, but is this necessary condition sufficient? Unfortunately, no. Consider this solution set. Notice that the sum of any two opposite vertices is 0, so it satisfies this necessary condition. However, if we try plugging this into our augmented matrix, a little row reduction will show us that it's impossible to realize this solution. That's kind of weird. I wonder if we can explain it geometrically. Consider the difference of any vertex on the top face and the vertex directly beneath it. So a minus e, or b minus f, c minus g, or d minus h. Pressing U will increase each of these differences by 1. Pressing D will decrease each of these differences by 1. And pressing B, L, F, or R will either change both of the numbers we're subtracting or neither of the numbers we're subtracting, either way leaving the difference unchanged. What I'm getting at is these differences are an invariant. They're always going to be equal to each other. We get this same result, perhaps less intuitively, by subtracting some rows in the matrix. And maybe you can convince yourself that the exact same logic works if we consider the differences between the 4 vertices on the leftmost face and the vertex directly right of each one, or the differences of the 4 vertices on the front face and the vertex directly behind each of them. It's pretty easy to see that these 3 sets of necessary invariants imply the necessary condition that we came up with earlier that was not sufficient. However, these 3 sets of equalities are sufficient, as we can prove by showing that any code that satisfies them is realizable. We'll do so by creating another Rubik's Cube algorithm, which I'll demonstrate on the original code that was given to us, but make sure that you're convinced that it'll work on any code satisfying our necessary condition. Our first step will be to set vertex A to its correct value, 4 in this case, by pressing face U. Note that because vertex A also lies on faces R and F, we can't use faces U, R, and F further along in our algorithm without messing up vertex A. We'll next set vertex B to its correct value by pressing face B. Note that this doesn't mess up the work we've done on vertex A. The only faces we have left to use that won't mess up one of the vertices we've already set are faces L and D. So we'll use L to set C to its correct value. And then we'll set vertex F to its correct value using face D. Our algorithm now guarantees that 4 of the 8 vertices are set correctly. However, our necessary condition is going to guarantee that the other 4 are also set correctly. To see how, consider vertex D. Note that D minus A must be equal to C minus B. So because A, C, and B are all set correctly, D must be set correctly. Similarly, vertex E must be set correctly. Because A minus E is equal to B minus F, and A, B, and F are all set correctly. To see that vertex G is set correctly, just note that A minus E equals C minus G. So A, E, and C being set correctly guarantees that G is set correctly. And finally, vertex H must be set correctly because, for among other reasons, A minus E equals D minus H, and we've already shown that A, E, and D are set correctly. What I'm saying is that our algorithm doesn't need any further steps. Anytime we satisfy the necessary condition, the code is realizable, therefore the necessary condition is also a sufficient condition. We're done with the 4th and final level. All that leaves is the challenge question. But this week, the challenge question is a little bit special. There's a math magazine that I've been published in before, to which I'm going to submit an article, basically recapping what we did in this video and the previous video. However, in the article, I'm going to talk about all 5 platonic solids. In these videos, I've talked about the tetrahedron, the octahedron, the icosahedron, and the cube. I have not talked about the dodecahedron. What your challenge question is to come up with the necessary and sufficient condition for a code on the dodecahedron to be realizable. I have a solution, but I'm hoping to come up with something more interesting. If you come up with anything that makes the article, I'll either shout you out in it or make you a co-author. Post anything you come up with in the comments.